This video is to be able to solve problems involving ropes and pulleys. We'll start by taking a closer look at the force of tension. This is Wally, the window washer. For Wally to wash the windows, he stands on a platform suspended by 4 cables. The tension in these cables balance out the weight of the Wally and the platform he is standing on, with each cable taking an equal share of the load. That is to say, if Wally's platform is at rest, then the net force acting on it must be 0. The sum of the 4 tension forces pulling up must match the sum of the weight of both Wally and his platform. If the platform had only 2 cables, the tension in the cables would have to be higher to balance the weight. Where is this tension coming from? If we zoom out a bit, we see that Wally is actually being held up by an elaborate pulley system, which is being anchored by his less animated coworker down on the ground. The cable is threaded through the pulleys, forming 4 vertical lines above the platform. These pulleys are assumed to have no mass. The only purpose they serve is to change the direction of the rope and thereby the direction of the tension force. Because the cable cannot change length, the tension force must be the same everywhere within the cable. Otherwise, the cable will be stretching out or shrinking. Let's take a closer look at that pulley system. The tension provided by Wally's coworker acts 4 times on the platform, in each case helping to lift this entire system upward. The benefit of lifting the platform in this manner should be apparent. If we assume the weight of the entire system to be 1500 newtons, about 337 pounds, then we see it will only take 375 newtons, or about 85 pounds, to hold the system at rest. Cables and ropes do have a maximum amount of tension they can have before they snap. If we assume Wally's coworker was lazy and picked up a very weak cable that can only support 500 newtons of force before breaking, then we can determine the maximum possible acceleration that Wally can have before the cable snapped. 1500 newtons corresponds to about 150 kilograms of mass, so we have a maximum upward acceleration of about 3 1/3 meters per second. His maximum downward acceleration has nothing to do with the strength of the cables. Rigging systems like this are common and useful, and allow Wally's coworker to exert minimal effort to hold up the system, which is perhaps why he looks so bored. Let's consider a more exciting system. A rope connects one climber on a cliff to another digging precariously off the precipice. This sort of system will tend to accelerate the hanging climber downward and the standing climber rightward. We want to know what the acceleration will be so that we can make it as small as possible. We'll model our system with a pair of masses, labeled small m and large m. We'll assume we know the coefficient of friction between the mass on the top and the surface. Always begin these problems by drawing free body diagrams, so as to identify all of the forces at play and the directions in which they are acting. Both masses have a force due to gravity pulling them down, and the top mass has a normal force holding it up. Both masses are pulled by the tension in the rope in the direction of the rope, and the top mass has a force of friction helping to slow everything down. Note the only way this system could be at rest is if the tension force T is equal to the weight of the hanging mass big mg. With the assumption that these blocks are accelerating, the tension force cannot be equal to the weight of the block. Now we need to pick a direction to call our positive direction. A convenient choice would be one that matches the motion the blocks would tend to follow. So let's go ahead and call the positive direction rightward on top and downward on the right, following the path of the rope. Doing this allows me to redraw the situation as a one-dimensional motion problem. Bending the path into a straight line, it becomes easier to see immediately which forces are acting in the positive direction and which forces are acting in the negative direction. Now, we apply Newton's second law for each block individually. For the small m block, the net force is equal to little m times the acceleration, which must be tension in the positive direction and friction in the negative direction. For the big M, the net force is equal to big M times the acceleration, which must be big mg in the positive direction and tension in the negative direction. There are 2 important realizations to make. The first is that the tension in the rope must be the same everywhere, so these T's are the same. The second is that because the rope does not stretch or shrink, the accelerations of both blocks must be equal to each other, so these A's are the same. Then, if I simply add these 2 equations together, I get a single equation without the force of tension involved. This I can easily rewrite to give me an expression for the acceleration of the blocks in terms of known quantities. As you might expect, to minimize the acceleration of the blocks, I need to try to maximize either friction or the mass of the block on top. Even if we take away friction, which is just the equivalent to setting mu sub k to 0, and so making all of these terms in red disappear, we can follow the exact same procedure to find that the smaller mass will still affect the acceleration of the larger mass. It is still beneficial to have as large a mass as possible on top to minimize the acceleration. In fact, this procedure will generally solve any setup for this type of problem. If we place the smaller mass on an incline instead of on a table, then we simply adjust our positive direction to continue to match the motion of the blocks, and factor in the component of the weight that is acting downward along the ramp, which quickly returns us to a similar looking answer as before. Instead of a friction term, we have a sine of theta term. If we let theta go all the way to 90 degrees, it would be the same as the mass hanging free, and the sine of theta term simply drops out of the solution.